Nice feeling.
Cool. Okay,
All
we're
right.
going to get started. So thanks for coming out, everyone. I'm excited to introduce Ted Pyne, who is a PhD student at MIT, where he's advised by Rodi Rubenfeld and Ryan Williams. There's some very nice work in pseudo-randomness and graph specification, vector specification. I guess he'll tell us about some pseudo-randomness stuff today.
All right. Yeah. Thanks everyone for coming. Yeah, I'm a second-year PhD student, and please, if you have any questions, ask them. I've tried to make this talk make sense, but I probably failed in some area, so we can like correct that on the fly. And the work I'm going to be talking about is primarily joint with Dean Duron and Roy Tell. And so the title of this talk is Hardness to Randomness for De-randomizing Space, and hopefully at the end I will have given some insight into all of the words that appear here. So let's. Oh, I need to say I'm okay with this being recorded, I'm guessing. Okay, good. So just for a brief overview, I'll first introduce this problem, this de-randomization tasks that we're going to be studying. Then I'll give a high-level overview of our results. I'll talk a little bit about some of the technical tools behind them. If we have time, which we probably won't, I'll go into more details about the proof of one of those technical tools. And then finally, I'll wrap up and bring up some open questions. And again, like if you have any questions, please ask. So what is the high-level computational task we want to solve here? We have some efficient randomized algorithm that solves some computational problem. Like maybe it's sorting something, maybe if it's checking a polynomial 0, et cetera, et cetera. Can we transform that algorithm into a deterministic, so algorithm which doesn't use any randomness, algorithm A prime that solves the same problem and is roughly as fast? So if we have like a polynomial time randomized algorithm, is there a polynomial time non-randomized algorithm that solves the same problem? So if we have like our source of random coins, we can throw them away. So there are two really well-studied definitions of efficient that are relevant for this talk. And the first is the goal of converting fast randomized algorithms into fast deterministic ones. So this is a very well-studied problem. There have been like pretty much decades of work at this point, just citing some of the literally hundreds of papers on this. And the central lens at this point that people usually use to think about this problem is this technique called hardness to randomness, which will come up a lot in the remainder of this talk. But there's a second de-randomization goal that is also relevant here, which is we want to convert low space randomized algorithms into deterministic algorithms that also use a low amount of space. And so maybe you've heard of the goal of proving RL equals L or something like this, like the capital letter statement of this. That's what we want to do here. And there's also been decades of work on this problem. And the central lens on this problem is a little different, but it's been given to us by the slogan of a large multinational corporation headquartered in Oregon, which is just do it. So this is a little strange, but I'll explain what I'm talking about here later. So just a quick overview of, for people who've seen this before, this will probably be a review, but how do we think about de-randomization in general? So we have a randomized algorithm, A, and we want to turn it into a deterministic algorithm, A prime. So suppose we pick some randomized algorithm that we want to de-randomize, and it's going to take two things. It's going to take an input X and some random bits R, and like use the random bits R to do some computation on its input. And we want to distinguish between one of two cases. The first is that most of the time, this algorithm accepts. It says like X is a yes instance. And when I say most of the time, I mean most of the time over the random bits. So everywhere in this talk, we're going to think of A as reading like n random bits and producing a yes or no answer. And so if X is a yes instance, it's going to say yes most of the time. And if X is a no instance, it's going to say yes only like 1/3 of the time, or something like that. And so if we could figure out which of these two cases we're in, we would be able to figure out, like, should we answer yes or no on input X? And so one way we can do that is by plugging in randomness, but we want to do that without randomness. And so what we're going to do is we're going to think of A like fixing an input X. So we want to solve this de-randomization problem on a particular input. And so if you fix a randomized algorithm with some advice in the form of this input X or a deterministic algorithm, you get a circuit, basically. So for the remainder of this talk, we can think of this problem, this circuit acceptance probability problem, or CAP, which is given some circuit, estimate the expectation of that circuit under random input. So this is like basically complete for de-randomization. Whenever we talk about de-randomizing, we're talking about solving CAP for some type of circuit. So how do we do this? One thing you might want to do is replace those n random bits with a many fewer random bits in a way that like preserves the expectation of this circuit.
So how's the circuit fit with randomness?
Yeah, so the way I'm thinking about this is we have a randomized algorithm which takes an input and which takes in a true source of randomness. And we know that when we give the circuit this true source of randomness, it does a good job.
Right, but
So they're just to the
yeah,
circuit,
but
right?
in
Yeah.
one log space, you shouldn't be taking randomness as an input. You should be feeding.
Absolutely.
The,
So
the gates need to be somehow randomized.
So the entire definition here is talking about randomizing general polynomial time algorithms. Log space algorithms will have an additional restriction, which I will talk about on a coming up slide.
But I have another question. If you want this generic, then well, PPP is already contained in p-poly, so there's nothing to de-randomize at the moment.
So we would like,
If your oracles come,
yes. So
maybe the audience, maybe the other members of this audience
Anyway,
don't necessarily know what it means.
so we can solve CAP using a polynomial size circuit. Absolutely. This is like, you know, P and P-poly. If we would like to solve this using a polynomial algorithm, like put it in P, would be, I guess, the more precise statement of what we want to do here. Yeah. And for the rest of the talk, we'll also be talking about like other goals, like solving CAP very space efficiently. Yeah. So good question. Hopefully addressing some of them, and I guess the slide after this. But to quickly pull back, like how could we hope to solve this problem? Is this even a reasonable thing to hope to solve? Well, to do a slight detour, it's not too hard to show using something called the time hierarchy theorem that algorithms which run for 2 to the n steps are strictly stronger than algorithms which run for 2 to the n over 10 steps. So basically, as you increase the amount of time you allow your algorithm to run, the number of problems it can solve like goes up by a non-zero amount. And so, okay, here's one conjecture or one assumption that you could make. Algorithms which run for 2 to the n steps are strictly stronger than circuits of size 2 to the n over 10. So up here I had algorithms versus algorithms. Here I have algorithms versus smaller circuits in some sense. So this seems plausible. Seems like it's probably true.
But wait a minute, algorithms are uniform, and circuit families are non-uniform.
Yes.
And non-uniformity can do a lot more.
Yes. So it's definitely the case that circuits of size 2 to the n over 10 can solve problems that algorithms which run for 2 to the n steps can't. What we're hoping for is that there's also the reverse, like the reverse non-inclusion. Yeah, exactly. So this class is definitely not entirely contained in this class. We just want one problem in this class that's not in that problem.
Yeah, a misnomer there.
Yes, yes. So, however much you want to believe this assumption, we have the following very cool result by Nissan Vigdersen and Ipagliazzo Vigdersen. Assume A1, this thing that I just wrote, then we can de-randomize all polynomial time randomized algorithms into polynomial time deterministic ones. This is this hardness to randomness paradigm. So, and just this is fast randomized algorithms, this is deterministic ones. So this assumption one seems plausible to me, but the problem is we have had not a ton of progress actually proving it. So in particular, it's been open for half a century to prove that circuits of size 10n, so not 2 to the n over 10, circuits of size 10n, can't compute any function that you can compute in like non-deterministic 2 to the n time. So we have a much bigger upper bound and we have a much smaller lower bound and we still can't prove it. So that these things are conditional results, but they seem like very solidly conditional. So in the regime of de-randomizing space-bounded algorithms, we actually have some amazing unconditional results. There's a result by Sachs and Zhou in the 90s, which was recently improved by Hosa, that says that for every randomized algorithm that uses log n space, there is a deterministic algorithm that solves the same problem that uses a little bit less than log to the 3/2 n space. So you can blow up at this like small polynomial cost, and you can de-randomize at the small polynomial blow up. And this result is unconditional. Like it is true right now. We don't need a hardness assumption. And the way we prove it at a stratospherically high level is to use many, many times that space-bounded algorithms are special, that we are not trying to de-randomize general polynomial time algorithms. So how do we use this special property? We first need to think about how space-bounded algorithms use their randomness. So let's take some algorithm that uses log n space on inputs of size log n. And again, let's fix some input x that we want to de-randomize. And now now the operation we want to do is we want to create this graph that captures how the algorithm uses its random bits. So like the algorithm starts computing, maybe with the all zeros tape here, and then it's going to read its first random bit. And if the random bit is 1, maybe it goes over here, and if the random bit is 0, it goes over here. And it's going to continue reading its random bits in this way until it reaches the end of the computation, where it's either going to say, I'm going to return 1, or I'm going to return 0 over here. And so we can think of this graph, which is capturing like how the tape is evolving over the random bits. And the thing that this results in is that de-randomizing small space algorithms is basically captured by producing pseudo-random walks for graphs. So if we can produce a set of random walks over this graph, which lets us estimate the probability that a random walk from here gets to here, then we will have successfully de-randomized. Because that's sort of the restricted computational problem that we're solving. And just to emphasize, we want to produce these pseudo-random walks very space efficiently. Like you could do something like breadth first search, but it would take too much space here. And also people in the literature call graphs read once branching programs, or ROBPs. I might verbally typo and use this, so just making sure that people know that those are the same thing. And sort of the very special property of random walks is that they're Markovian. So if I tell you that in the computation we've reached here, you essentially no longer care how we got there. You don't care if we took a walk through this or like through this or something like that. And in particular, what that means is each random bit the algorithm is reading, like here it reads the first random bit, here it reads the second, each of those random bits is only used once in the computation. And this is the fact that these random bits are only used once and only used to take a random walk over the graph is really a severe restriction on these algorithms.
But that's not in general true of log space, because I can choose if I'm a log space algorithm to remember this random bit. Would that be?
So great. This, once we're here, how much information are we storing, basically?
Exactly.
We're storing order log n bits of information, and how do we capture this in this model? This graph is not of arbitrary size. If we think of having one state per configuration of the algorithm, in the end, we're going to have like, n to the something different states. And because we're doing complexity, I'm just going to assume that n. So like producing random walks for graphs of size n is the problem we're working on here. Yeah. And so this quote read once property that we're taking a random walk on a graph is behind every unconditional advance in de-randomizing small space algorithms. And there was a prior belief that the hardness to randomness paradigm couldn't leverage this property, that these two different approaches were in some sense distinct. For instance, there was this really great recent survey of Hatami and Hosa on unconditional pseudorandomness that said the hardness to randomness framework is not well suited for the important problem of essentially de-randomizing log space. Another glass half empty thing was that these prior works studying the hardness to randomness paradigm for space-bounded computation also de-randomized stronger models that don't have this read once property. And those stronger models, like unconditional results, seem quite out of reach. So the key conceptual contribution of this work is we show that the hardness to randomness paradigm can leverage special properties of small space algorithms. And by doing so, we obtain de-randomization from new qualitatively weaker results. So now I'll give a bit a longer statement of our results. If anyone has questions, you can ask now. Otherwise, I'll go on. So our main result shows that we can combine the random walk and hardness to randomness perspectives and get de-randomization from new and qualitatively weaker assumptions. To go into briefly more detail, there was this work of Clivens van Melkebeek, building on some prior hardness to randomness work, that said that de-randomization follows from there exists some function or some language L that's computable by small space algorithms that cannot be computed by small circuits. So we need one language that has this property. Our main result is essentially the following. De-randomization follows from the existence of a language computable by small space algorithms that cannot be computed by small circuits that are themselves produced by deterministic small space algorithms. So here there's a language that you can compute using a small space algorithm that you can't compute using a small circuit. Here, there's a language computable by a small space algorithm that can't be computed by effectively some model of uniform computation. So there's an algorithm which is printing a circuit, and then we're like evaluating that circuit. And that circuit needs to be small, and the algorithm needs to be deterministic in small space. And so if there's one conceptual takeaway here, it is this is not a circuit lower bound. Like this requires proving something can't be computed by any small circuit. This is not any small circuit. This is fundamentally a uniform upper bound versus a uniform lower bound. We're just trying to like duel these against each other. So again, this is just the...
Sorry, just to make sure I understand it correctly. So the assumption is that somehow if you want your small space algorithm to compute L, no problem.
Yeah.
But if instead you wanted to first give you a circuit, a small circuit,
Yes.
that will then compute L, then forget it.
Yes.
Right? So it directly computes L, but not the circuits that will then compute L. So it cannot somehow communicate its wisdom to the small circuit.
Exactly. Yes.
Okay.
And just to computable by small space algorithms, deterministic.
Yes. Yes. Yeah. Both the upper bound and the lower bound here are deterministic small space
Right.
algorithms.
I see it in the
Yes. Yeah.
in one, but not the other.
Good. Yeah. And this is as close as we're going to get to a formal statement because the formal statement of these results are quite involved and actually refer to like even weaker classes. Like it's not a general circuit; it's a restricted class of circuit that it prints, et cetera, et cetera. But this is the idea, pretty much.
And you're gonna at some point, we're not gonna necessarily see it, but you prove this variant of that statement.
Yes. Yeah.
That-
Wait.
Yeah.
No. That's
Oh,
a
sorry.
gesture. This is like a gesture.
Yes. Yeah.
you
Sorry.
Still have to assume it.
Yes,
Yeah.
we do not prove this. Yeah, this is a uniform lower bound that we have not proved. Yeah.
He
Okay.
said
The-
that's
It's still not,
necessarily evil.
it's still not conditional. It's still conditional.
Yes, it is still conditional. Yeah. That's
But
very
we
important to
use
emphasize.
This hardness to randomness paradigm
Yes.
to
Got
prove
it.
it, which is the
Yeah,
first
it's a
time
methodological paper
that
rather than.
this paradigm
Okay.
applies in this
Yeah.
small space. Like,
I guess as a spoiler, like the final open problem on my open problem slide is like actually prove this assumption and conclude that we can de-randomize space-bounded computation.
yeah, but the Clivens on Milky because there's also an assumption of it.
Yeah. Yes.
So,
Exactly.
so like,
There's some progress maybe if you think about it that way. So just to slightly explicate stuff that already came up in the questions, this is we need de-randomization and we get lower bounds for classes that we can already prove non-matching lower bounds against. So that the lower bounds that we can prove are not strong enough to what we need, but they're at least reasonably strong themselves. And closing such a gap has actually been done in like other types of lower bounds for uniform algorithms. So we proved some other results using our techniques. And one thing that we address is the question of whether we can de-randomize with very low space overhead. There was this recent work of Doron et al., which said, assume some hardness to randomness type thing here that I'm not going to explicitly state, and that there exist highly explicit cryptographic PRGs. So like this is just a, the notion of a PRG from cryptography. If you additionally assume that the PRG is computable by, for instance, constant depth circuits, that's the type of assumption they want. Then we can turn every space S randomized algorithm into a space 2S plus order log n, where this is some global constant deterministic algorithm. So we can basically de-randomize at a cost of a factor of 2 blow up. We prove the exact same thing, getting rid of the crypto. So we're able to show that make some standard, albeit high-end, hardness to randomness assumption, then you get the exact same conclusion. And in the time-bounded case, it's not really known how to get this high-end de-randomization from standard hardness to randomness assumptions.
Wait, and the star that is your assumption,
Yes.
right? And the prior work already made the same assumption?
Yes, it is literally the same assumption. Yeah.
So the assumption in your work is not new. You inherited from this other paper.
Yeah. Or to be clear, this is not what I put on the previous slide. It's a different assumption.
Oh.
Yeah.
Okay. So, but
He's
there
just
is
not telling us what.
Oh,
Yeah.
okay.
It's that secret assumption.
This is okay. I'll reveal the secret and spoil the fun. This is basically, there's something computable by algorithms that isn't computable by circuits that are only a little bit smaller. Yeah. So it's like a standard hardest to randomness type assumption, but it's very close. Like it's a close run thing on how big the circuit can be. And so yeah, we eliminate the crypto assumption in this result at no cost. And again, in order to eliminate this crypto assumption, we're going to use this random walk perspective and actually some really recent work on PRGs for like different types of branching programs. And there are also more results which are in the paper.
It's not everybody here is a crypto fan. You should just say what a PRG is.
Yes. PRG is a object which is going to stretch like some number of truly random bits to a larger number of random looking bits. This is an object which will come later in this talk, but we can cryptographic PRG, which is I need to produce the output of that PRG, and then even if you have like much more time to break that output than I have to compute it, you still can't. So
It stands for
pseudo-random generator. Yes.
Yeah, that's it.
Sorry, stretching a few number of true random bits to a lot of random looking bits. Yeah. And so now I'll talk a little bit about the technical like framework that the paper is in and some of the technical tools that we develop. And so in order to do that, I have to give the hardest to randomness recipe. So what is like this hardest to randomness perspective? One, or sort of the way we might think about it is we construct a pseudorandom generator, so same as what came up there, that stretches order log n bits to n bits. So this has an exponential stretch. We're taking a really small number of truly random bits to a really large number of pseudorandom bits. And in order to instantiate this generator, we need to give it a truth table. So this truth table F, honestly, you can just think of it as a string of length, poly n, pretty much. We can think of it as like the output of some function on log of that many bits. So like you give me an index and then I give you f sub I, basically. It's like the output of some function, but for the purposes of this talk, we can think of it as a string of polynomial length. And this generator has the following property. Suppose we are given a circuit which distinguishes that generator from true randomness. So we look at, how often the circuit accepts a uniform input, and we compare it to how often the circuit accepts an output of that generator, and these things are different. So this is like the generator is not doing a good job approximating true randomness for this circuit. Then there exists a small oracle circuit, C, such that blah happens. So what is blah? Gives C the ability to ask B questions. So C has the ability to ask B, like, can you return your value on string X or something like that? And other than that, C is honestly not doing that much. And then you give C an input x, and it computes like the xth bit of f. So again, this is like it's basically computing the string f with the ability to ask queries to B. And so in particular, if B is a small circuit, we can think of basically including the code for B inside C. Like rather than thinking of it as being Oracle queries, we just like wire in the circuit B.
Wait, does it really compute all of it correctly? I thought it's being allowed to do this.
So the original version of this computed it most of the time. It was able to be boosted to compute it all of the time. Yeah.
Oh, wow, okay.
So I'm saying NW. I should probably be saying IW here.
Okay.
Yeah. But yeah, it's so we are asking for like worst case correctness here.
So yeah, going back to the beginning, the sentence starts exists. So are you asserting the existence? Are you hypothesizing the existence? Are you assuming?
People 20 years ago constructed a pseudorandom generator with the following property. Yes,
Okay.
This is the Nissan Wigderson and Impagliazzo Wigderson construction.
Okay,
Yeah.
that's what the NW and I.
Yes.
Got it.
Yes. Sorry for the quantifier
Inside
mishap there.
baseball. Yeah.
But yes, so this is a generator which everything I'm writing down is true. Like these results have been proved and were proved a long time ago. And so if we have that this circuit B is small, there is some small circuit which computes F. And so basically our classical de-randomization assumption is something like we have access to a string F which doesn't have any small circuits. And what does that mean? Just sort of applying the contrapositive. That means that it never happens that this PRG is broken by a small circuit. Question?
When you say small, what does that mean?
Yeah. Maybe let's think of this truth table is of length n to the 100, and this circuit is of size n to the 10. So this is like a much smaller polynomial than the other one, basically. Yeah. Although, yeah, at least that's the sort of range we're applying it in.
I'm still having trouble parsing. So what is the quantifier on F? That is, there exists.
Any.
Yeah, so the pseudorandom generator takes in any string you want to give it. So this pseudorandom generator, which other people constructed, you give it some string f,
I see.
and all of the time, if you break the generator, then yes, for that particular f, exactly. And so our classical de-randomization assumption is basically just the contrapositive of that. Assume that we have ourselves access to some string f that doesn't have any small circuits. That means that the PRG isn't broken. And that means that we can use the output of the PRG to estimate the acceptance probability of this circuit under a random input by computing its acceptance probability under the generator and then, like rounding, basically.
Yeah, I know this doesn't solve your problem, but for example, if F were truly random string, it's probably has no small circuit.
Yes,
Yeah.
exactly. Yeah.
So this was used by Luca Trevisan to construct this amazing breakthrough in randomness extraction. Right? So that like unconditionally, if you have enough of an entropy in a string, you apply this and you could extract the tree length.
Yes, exactly. Unfortunately, I won't have time to talk about the extractor side of things, but I guess there's one sort of worry about the assumption that was happening here. Oh yeah.
Can you go back to the last slide and then just go for it? When you say PRG isn't broken, because the contrapositive means that there does not exist such small. And how does the surge implication work? Sorry, I'm not.
Yeah,
I'm
so
missing something. Yeah.
there's no small circuit that has this property. And what that means is the expectation of B under this distribution is always a pretty good estimate of the expectation of B under this distribution.
For all small b.
For all small b, exactly. Yeah, so given a small b.
And this is something with the rectifier.
Exactly, yeah. We're given a b that we want like an estimate of the acceptance probability of.
Might as well just take this random thing.
Might as well take this estimate and then use that, yeah.
Right, so which basically says here I'm gonna use this PRG to run it on my input X and see whether it's more than 2/3 or.
Exactly. Yes, exactly. Yeah,
As long as F has a small circuit is fine. Okay,
exactly.
sure.
Yeah. And I picked the constants so that like 1/3 plus 1/10 is different from 2/3 minus 1/10. Yeah. So that's exactly the recipe. But there is this little question, which is we're assuming that F has no small circuits. Like, and this is because just applying the contrapositive operator to this statement, we get that we need to assume that F has no small circuits. And so even if the circuit for F is so like strange and magical that it could never appear in our actual de-randomization problem, this is still a problem. Like we're not, we really need to assume that there's nothing that exists. And so this is forcing us to make a non-uniform hardness assumption. We need to say that we have access to a string F that no circuit can break, and this is sort of resulting in our use of circuit lower bounds here. Our main contribution is to prove the following. If B is a space-bounded algorithm that breaks some instantiation of this generator, we can construct in deterministic log space a circuit C such that C is a small circuit for F. So now we're saying rather than a circuit C exists that successfully computes the truth table, we're saying once we have our hands on an algorithm which breaks the generator, we also have our hands on a small circuit for the original truth table.
Well, actually, before you move on.
Yeah.
Can you tell us who the letters are?
Oh, yes. So this Dean, myself, and Roy, which is the title of the talk, and then a previous work of myself, Ron Raz, and Weizan also constructed a very similar object. Yeah. And in fact, at this high level of generality, these works achieve this goal. Yeah.
And I assume it's not log space star. It's log space with an asterisk.
Yes. Yes. We actually construct a bunch of circuits, or like polynomially many, and one of them is good. At least one of them is good. In order to check which one of them is good, we need to compare against F, basically. Yeah. So this is like the one detail that I was hiding there. And so our new assumption, again at a sufficiently high level of generality, is that we have ourselves access to a string F that has no circuits that can be constructed by deterministic log space algorithms. Because this, again, is just pretty much the contrapositive of this statement. And so there are two components of this result. So here they are. The first is we give an efficient, by efficient we mean deterministic, transformation of B, which again is the circuit that breaks the generator, the small space circuit that breaks the generator, into a, quote, predictor for the generator. And this is something that I'll define on the next slide. And the second thing is we give some new locally decodable codes with very randomness efficient decoders. So, what's the time, by the way? So I'll quickly talk about what are the, some more words about both of these technical tools. And the first, which is this transformation of a distinguisher to a predictor, is this really nice transformation known as Yau's lemma. And so this also comes up in all of the previous hardness to randomness works, which is, okay, I'm now going to give a definition, apologies. We say that a circuit P is a previous bit predictor for a distribution if P takes in, like we sample some X from this distribution, and we give P like the final 10 bits of that string, and we ask P to predict the 9th bit of that string. So we give it access to a suffix of the string, and we ask it to predict some bit that we haven't given to it yet. So it's worth noting, if this is the uniform distribution over n-bit strings, you can't do this any better than 1/2, any better than just guessing 0 or guessing 1 or something. And so we're going to ask this predictor to do a little bit better than 1/2. we're going to ask it to predict with advantage maybe like 1 over n, something like that, 1 over 10n here. And so there's this lemma called Yau's lemma, which says, given a circuit B that distinguishes between between this distribution and the uniform distribution, there exists, with the alarm bell emoji around it, a circuit P that predicts this distribution, and that circuit is, almost the same as B. It's very close in size. So our first technical contribution is, given a space-bounded algorithm B that distinguishes between some distribution and the uniform distribution, we can construct this predictor P in deterministic log space. And again, this is every time a phrase like this appears in the hardness to randomness proof, we need to get rid of it, because this there exists will force us to make some form of non-uniform assumption. And so we show that we can find this predictor much more efficiently. Our second main contribution relates to this goal of the hardness to randomness paradigm, that create a circuit that correctly computes this string at all positions. Like no matter what index, it correctly computes f sub I. So after we transform our distinguisher to a predictor, and then we do some trick using combinatorial designs, we get a circuit that computes f basically slightly better than average. So you can always compute a string in 1/2 of positions by always outputting 0 or always outputting 1. Here, we're doing a little bit better. So this is just an average case notion. And we want to go from computing f on average to computing f at every index. And the way we're going to do that is we're going to pull out this error correcting codes hammer. So implicit in this work of IW was a statement that there exist locally list decodable codes. If you don't know what that is, don't worry about it. That are list decodable from agreement, basically 1/2 plus 1 on the previous slide, where that force us to the parameters here. Basically, if you have the ability to compute something in this fraction of positions, and you have a little bit of advice, you have the ability to compute it. You have the ability to compute the original message everywhere. So this is like precisely the tool that we want to go from average case to worst case. Unfortunately, the decoding algorithm of this paper is randomized, which we don't have access to, and uses too much advice, which we also don't have access to. Our second technical contribution is to show that there exist locally list decodable codes with good parameters, roughly those of previous works, that are decodable by deterministic log space algorithms that have only log n bits of advice.
What is advice in this setting?
Yes, so great, yeah. We have the ability to compute this correctly most of the time, and we are going to transform that into a bunch of different guesses for the original string. There's going to be relatively few of these guesses. Like it's not going to be a giant list, but there are going to be like many candidate original strings, and the advice is going to say that one is the right one, basically. Yeah, the advice is an index into a list which says which of your candidate decoders was correct. Yeah, which of your candidate decodings is correct. Any other quick? This will be the last time coding theory appears in this talk. So if you don't want to parse this, it will matter. And this builds off work, both the PRZ work and this work of Duran et al. From earlier in this year. And actually, these things are decodable by an even weaker class that won't come up. So putting these two technical tools together, we get a new instantiation of the hardness to randomness paradigm, which looks like this. We again unconditionally construct a pseudorandom generator that stretches log n bits to n bits, that is again given a truth table. And given a read once branching program, so a space-bounded randomized algorithm that breaks this generator, which is exactly the definition before, we can find in deterministic log space a small circuit such that the circuit with access to this RRBP computes the original truth table. And so our high-level new conclusion is that if we assume that we have access to a string f that has no small circuits that can be found by deterministic log space machines, we can conclude derandomization. So let's see. Sorry, how much time again? 42. Okay, so I should have, I'll be able to go into the details of one of these things. So it turns out that this proof that we can turn a distinguisher into a predictor is really simple and really nice. There were more complicated proofs of this before, but I think this is like a nice version of it. So recall that, we know from Yao that given a circuit that distinguishes between this bad distribution and the uniform distribution, there exists a circuit that predicts the bad distribution with some advantage. And we want to find that predictor. So we want to get our hands on it. The way Yao's lemma is proved is via the hybrid argument. And what we're going to do is basically define a sequence of distributions where for the ith distribution, we plug in uniform bits for the first I-1 bits, and we plug in our bad distribution after that. So we're sort of sticking the distributions together and sequentially replacing the good uniform distribution with the bad distribution D. And we have at the start that the expectation
I is going up,
yes.
so you're getting more and more bits of randomness as I goes up?
Yes. Okay. Yeah.
Okay. More truly
Yes.
random bits.
Yes. If it may make sense to flip these if I wrote it in the wrong direction. Yes. And actually, you need to consider both directions because you'll note that I've already dropped an absolute value here. But you define n+1 distributions, and one of them is too high and the other is too low, and then we step between them. And so if we know that the gap between the first and the final distribution is greater than 1/10, or the expectation under first and final, then there's some point I where the expectation jumps by more than 1/10n, because that's like the number of steps we took. And so we can start rearranging here, where we can think of sampling a uniform string z, and then sampling a string xi. And I worry that this is not the best use of everyone's time, but we can basically rearrange this expression, replacing some stuff with some other stuff, and we eventually get a candidate predictor that looks like this. We're going to take a random string z and a random bit b, and we're going to ask this circuit b to compute what it would output on z followed by b followed by the final bits of x, which recall is the thing we want to predict.
Specific I that get the alpha.
Yes, exactly. Yeah, there is some good index I where we're going to cut the distribution off after I and replace it with x, and we're going to try and predict the ith bit of the I plus first bit of x. Yeah. Oh gosh, that should be I-1. And so the candidate predictor that we get is see what the circuit outputs here. If the circuit outputs 1, flip b and output that as our prediction, and otherwise don't flip b and output that as our prediction. And so we can rearrange and find that this results in us getting a prediction advantage of exactly what we want. And so what we have here is basically a distribution over these predictors, because this z is like a uniformly random string. And we know that if we pick this string at random, we get like a pretty good advantage here. And so yeah, in expectation over the ways we could fill z in, we get a good advantage. And therefore, there exists a fixed choice of z and b such that p sub zb is a good predictor. And this is like the proof of Yao's lemma.
And also I.
Yes. The nice thing about I is there are only n choices, and so you can try all of them. Yeah. But yes, absolutely. There is a
Well, so B, there's only 2 choices for B.
absolutely. The actual problem is z here. Yeah. Frankly, I could have just said, yeah, there exists z such that p sub z is a good predictor. So a question we could ask is, can we find a good predictor given our distribution over predictors? A glass half empty result here is that if B is a general circuit, finding such a good predictor without using randomness is probably very hard. And in particular, it would imply like magical complexity results like BPP equals ZPP. Like you can make all randomized algorithms 0 error. The glass half full perspective is that if something is hard for general circuits, and our goal is to use special properties of small space algorithms, this might be a good place to use that our target is not a general circuit. Because we're not actually dealing with a general circuit here. We're dealing with a graph or a read-once branching program. And so now we're basically just going to peel away all of the definitions and see what Yao just said. So recall that randomized space-bound algorithms just correspond to taking random walks on graphs, pretty much.
That was like 40 years ago.
There's,
But yeah.
yeah. No, I mean, and we're going to peel it away for a very specific type of adversary here. And so let's recall that, by this probabilistic argument, there's some good predictor out there in space. And the good predictor looks like this. It looks like you take in B, you fill in some bits with Z, you fill in some bits with B, and then you fill in, the remainder bits of your pseudorandom distribution. What is B doing? B is taking a random walk on using its input because it's a space-bounded randomized algorithm. Fixing the first bits of a random walk to a string has a simple interpretation in terms of the random walk. It's starting the random walk somewhere else. So rather than starting it from like the start point, we're going to wander around the graph using our good predictor info and then start from there. There are only n different places to start a random walk on a graph. There might be 2 to the n ways to get to that place, but there are only n different places to start a random walk. And this is basically the Markovian property of random walks. Once we know where we are, we no longer care about the previous bits or how we got there. Because there exists some good prefix z, there must exist a good place to start the walk that gives us a predictor with good advantage. So that is the complete proof of one of the key technical tools in our paper. The other key technical tool has a longer proof, unfortunately. But the thing that we get is actually this new object called a distinguish to predict transformation. We called it that. For every ROBP, or graph, there's a collection of these candidate predictors such that for every bad distribution, so for every distribution which fails to fool this branching program, there's some predictor that predicts that distribution. It turns out these objects have sort of implicitly been studied before in like a work of Nissan and a work of Cheng and Hose. But we pull out the definition here and give a new construction. And this object kind of seems interesting in its own right, like the ability to certify that a distribution is bad. And in fact, in some follow-up work, we show that if we don't care about the de-randomization being space efficient, this is actually all you need to de-randomize. The existence of this object alone implies very non-trivial de-randomization. So finally, I'll just summarize what just happened. We show that we can combine 2 very well-studied lines of work, the hardness to randomness perspective and this random walk-based de-randomization of small space algorithms, to obtain de-randomization of small space algorithms from lower bounds for uniform deterministic models. And so, okay, just as a final thing, where could we go from here? First natural question is, can we get de-randomization from assumptions? Like, can we push these trade-offs further? Could we show that there's some type of lower bound that holds if and only if you can de-randomize space? So these sort of connections in both directions between space-bounded de-randomization, between time-bounded de-randomization and lower bounds are known. In the space world, it's open to get like interesting lower bounds out of proving RL equals L. And finally, perhaps most optimistically, could we actually prove these assumptions and conclude unconditional de-randomization of space-bounded computation? So thanks, and I'll be happy to take questions.
In the space of how close are the conditions to some of these conditional lower bounds proven? Like, what are the strongest conditional statement or strongest statements that look most like the conditions of the conditional statements that we do know?
Yes. We give sort of two big main results. I was basically presenting the second. The first looks something like function small constant depth circuits. There is a function computable, a log space algorithm that is average case hard for no, even stating that is not great. Okay. The bound that I'm presenting, like there exists something computable in linear space that is hard for linear space algorithms that print circuits of size 2 to the epsilon n. You can't prove it by diagonalization because you need something that you can compute in space 5n that is hard for space 6n algorithms which print small circuits. Like that's why you can't sort of conclude the de-randomization immediately, but similar gaps have been overcome in other settings. But that is like the most plausible looking assumption that you can conclude de-randomization from.
No, I'm good. I asked one question.
Any other questions?
And yeah, if anyone has questions, like email me. So
Okay, yeah, let's think that again.
thanks.